Hello everyone. I'm Giuseppe Maggiore, for those who don't know me. And I'm going to start now recording a TypeScript introduction. So, as you can see here on my screen, I have already set up in Visual Studio Code a TypeScript project. Now the TypeScript project is going to run in Node.js, which is the JavaScript, the JavaScript engine that we can use for simple applications like the one I need. We have a package.json, which only has a dependency, so should be a dev dependency, but yeah, okay, for this project doesn't really matter. TypeScript. The entry point of the application will be the /out/app.js file. We have two scripts, one for building TypeScript in watch mode, so that we just run it once and it keeps recompiling our files as they change. And then whenever we start the application, it simply runs the out app.js file. There's also a tsconfig.json file, which contains all the options for TypeScript itself. Let's look at the options we have enabled. Now, the kind of language support we can expect from the underlying compilation. Module is not very relevant. Declaration and declaration map and source map means that as TypeScript is transpiled into JavaScript files, we're going to keep in some special files with, you can see them here, .d in the extension. We have the definition of all the types that would otherwise be lost in the JavaScript file. And the declaration map is a mapping file that tells which definitions correspond to which JavaScript entities. Source map generates the app.js.map files, which tell which constructs in the JS file correspond to which original constructs in TypeScript file. So this is the most complete way of preserving as much information from the original TypeScript file as possible into the compiled result. Outdir means that we want all the compiled stuff into a single directory, which is the out directory. There is no special reason for calling this out. I call it out because it's the output of the compilation, but yeah, you could call it bin or whatever. This way we keep the source files neatly separated from the compiled files. We're compiling in strict mode. It means that the compiler is not going to show us any leniency. If we do something that is unsafe for whatever reason, that might break, that might at runtime end up in an invalid state, strict is going to have the compiler throw an error. And finally, we exclude the node modules, which are all the JavaScript dependencies. We don't want TypeScript to try to compile them, and we also exclude out from the compilation because obviously these are the files that we compile into, and TypeScript shouldn't include them as the input of the compilation. Let's move to our app.js file. Let's close the sidebar. As you can see, the file is not particularly exciting right now. We simply have console.log hello world, and we can run this as follows. And there you go. Now it's it's running. Okay, so let's start by defining some variables. Let's define a variable, the name, and well, my name is Giuseppe. Now, first name, because name is apparently a variable that's already declared. Okay, now let's take a look at what TypeScript knows, because you might wonder, okay, in this sense, TypeScript is nothing special. It's looks the same as JavaScript or Python even. But let's take a look at what the IntelliSense knows, and it says, oh, the const file name, first name is literally Giuseppe. Okay, it's interesting. Let's put a type annotation though. Now it says the first name is string. That's intriguing. We'll get back to that. And this is, well, clearly not JavaScript ish anymore, because, well, now we're not just saying the first name is Giuseppe, but we're also stating that first name is supposed to be a string. We could also say that first name is supposed to be a number, and now we get the first error, because TypeScript is helpfully telling us that Giuseppe is not assignable to type number. It's actually saying type Giuseppe. Again, wonder what that means. We could also say, well, boolean, trying another type. Obviously, that's also not going to work. Let's go back to string, and now TypeScript is happy again. Const last name, string, and my surname is Maggiore. And in the console.log, we could interpolate a string which says hello, first name, and then we also put the last name. No, we don't need semicolons. Okay, and now I'm going to run. I'm going to move the recording, the camera thing here, yes, so that it doesn't bother the console. And there you go. Hello, Giuseppe Maggiore. That's nice. That's handy. So let's put my age in here, and my age is 35. Oh, sorry, number. And the age is 35, and then when we put here the age, and at this point we get, well, hello Giuseppe Maggiore, you are 35 years old. And there you go. Okay, easy peasy. Now let's explore this typing thingy a little bit longer. So if we take a look at the app.js file, you see that, well, all the type annotations have disappeared. Well, the code is the same, but the only thing that's been stripped out are the type annotations. So in some sense, TypeScript requires us to be quite strict in declaring our intention with respect to what things are supposed to be, but JavaScript is simply going to ignore all that. So TypeScript is going to verify that our intentions match our code, and if TypeScript actually gets to be happy about the code we've written, it's going to simply strip all these things and generate JavaScript, which looks very much like the original TypeScript without any type information. Okay. Now, we can perform some operations. So we could also say that the output string is hello plus, because this is slower obviously than building the same string with interpolation, but bear with me. Okay, so now obviously this makes sense. But what if we were to add the age as well? No, it's also happy because the age can be converted automatically. Okay, so that's also quite nifty. Now, let's do something a little bit more abstract now. Let's say that we have a variable, and let's say that this is, yeah, again, my name, Giuseppe Maggiore. Notice that it's not really guessing. So now we can ask what it thinks x is. And it says that the type of x is Giuseppe Maggiore. It's not saying it's string. What if we put true here? And again, notice that it's saying it's true. What if we put 24? And here it says that the type of x is the same as the value. It's 24. And we can say to TypeScript, no, let's be more general. X is a number, and this is also true, obviously. So what this suggests is that the type language of TypeScript is far richer than just a string, number, boolean, etc. We can do more. Let's explore this a little bit. Given two types, given any value, we can say that a value can be promoted to being a type. Let's say that we want to have variable x, and we want to state that variable x can only be 0, 1, or 2. And I can say that x is 0, as type 0, and now we get a compiler error. Why? Because, well, we're stating that x is only going to be 0, and we try to put 24 in it. So we really have to put something that's compatible with the type, and that's 0. Types, in a sense, identify a series of values, and if you try to put a value that doesn't have the right type, then TypeScript is going to complain. But what we wanted to say was that x is going to be either 0, 1, or 2. But the compiler is happy because when we say that x is going to be either 0, 1, or 2, and we put 0 in, and that's great. We can also put 1 or 2. Let's turn x into a variable, and if I later say that x is 0, it's also happy. X is 1, also happy. X is 3, not happy. And, well, it's saying that x is supposed to be 0, 1, or 2, and 3 can't be assigned to type 0, 1, or 2, because 3 does not belong to the set of values 0, 1, or 2 that are identified by the type. We could also say, now, we could also do something a bit silly, because now, well, x is going to be 0, 1, or 2, or a number. And notice that the compiler is smart enough to notice, yeah, but 0, 1, and 2 are numbers. So if you say you're 0, 1, 2, or a number, well, that's kind of the same as saying you're a number. That's nifty. But we could also say it's either 0, 1, or 2, or a string. Now, 2 is allowed, 3 is not allowed, but a string, hello world, a string may be put in there. What about true? Not allowed. Why? Because true is neither a string nor it's 0, 1, or 2. Quite powerful. According to the very same mechanism that's allowing to say that x can be specific values like 0, 1, or 2, we can also use strings. So you could say that x is, well, you could imagine that we use strings for the flags. So this is loaded or unloaded. And then, well, what can we put here? Notice that if I just put the quotes, then the IntelliSense is telling me, yeah, that can only be loaded and unloaded. What if we try to put 3 in here? Obviously not. What if we try to put something else, like valid value? No, because even though, well, loaded and unloaded are strings, we're saying that x is not really allowed to be any string. It's only allowed to be these very, very specific strings. Okay. Now, that's enough for the very, very basic introduction of TypeScript, and now we'll move on to some more complicated typing constructs. We've seen very simple types, and it's interesting to notice that there's a richer type language that allows us to give names to types. For example, the type valid flag, we could state that valid flag is the type that is either valid or invalid. And, or, yeah, validity. And now I can use this type whatever I want, or whatever I want. So I could say that x has type validity, and now if I invoke the IntelliSense, it says, okay, then you can either be valid or invalid. Let's be positive, let's say that it's valid. Now, another sort of type we can define is the type that governs an object. I could say that the person object has name, which is a string, the surname, which is a string, and an age, which is a number. And I'm simply defining a structure. I'm defining that if something is supposed to be a person, then it must have exactly these three things, and they must have the correct types inside the object. So if I state that P is a person, notice that I also get a lot of advice from the IntelliSense, because, well, if I press Ctrl space, then, well, I get to fill in the name. Yeah, let's stay with the autobiographic theme, Maggiore, and the age is 35. Okay, great. Also, if we were to define a function that takes as input a person P, and check it out. Now inside P we have the age, the name, and the surname. So I could do a console log of P dot name. Again, pretty nifty. Now suppose that we know that a name always has these things, and then we want to define the roles within an organization. So suppose that we have, let's say, a developer, and we want to state that the developer is a person, obviously, but they also have some other attributes. Specifically, let's say that a developer has a preferred discipline. So you could say that the developer is a person, and notice that we have now another type operator that's, well, not the same as OR, but, well, in the sense of being a type operator it is, but in what it does it's different. And we say that the developer is a person who also has a favorite discipline, and let's say that the discipline is going to be front end or back end or DevOps. Not really thinking very hard about proper development disciplines here, so just bear with me. Now we could say that we have an operational person, no, an operational team member, and we could say that in their case the favorite discipline is, or the focus can be project, delivery, or service. Even call it operational manager. Yes, so we have project managers, delivery managers, and service managers. Okay, and now let's state that a team member is either a developer or an operational manager. Now let's throw our old example away, and, well, let's say that, say my name takes as input T, which who is a team member. Let's take a look at what's here. Now in T we have, well, we only have age, name, and surname. Now it means that we can still write console.log t.name, so at least that's good. But we can't say anything about the favorite discipline or focus of this person, which also makes sense, because if we know that someone is a team member, we don't know whether or not they're an operational manager or a developer. Let's add some extra information to this. Let's say that in the developer we have a kind, and the kind is dev. And in the case of the operational manager, the kind is opmgr, operational manager. So if I take a look at what's here, now we still have age, name, and surname, but we also have kind. And kind, well, what's kind? I'm going to invoke the intelligence here. Kind is going to either be dev or operational manager. So what can we do with the kind now? We know that the kind is dev or op manager, and, well, that's kind of the only hint we have in order to get to the information specific to someone being an operational manager or someone being a developer. And the only thing we really can do is we can check what kind we have. So here we know that the kind, well, it's either dev or operational manager. Okay, well, let's go with it. And let's check what happens inside the if. And bam, there you go. Now we have age, kind, and name and surname. The kind is now just dev, because we know that inside the if, well, if the condition was true, then kind is dev, so it's not going to be operational manager. And we have the favorite discipline, but we do not have the focus, which really makes sense. So now I could potentially check, print the favorite discipline, and if we take a look at what the intelligence knows, it knows that the favorite discipline is not just a string, it's either front-end, back-end, or DevOps. Let's put an else here. And, well, here the kind is op manager, because it knows that in the else, we only end up in the else if we are an operational manager, and then we have the focus, and the focus is going to be either project, delivery, or service. And obviously, in the else we don't have the favorite discipline, because this person is not a developer at this point. We could also be even more verbose. We could check the kind, and now the kind, it knows. You can see it from the intelligence that this is an operational manager. Here we have the focus. Let's put the focus in here. And in the else, oh, there's nothing in T. Because in the else, T has another type, which is never. Never means it's never going to happen. this piece of code, line 25, is never going to be executed because the type system can guarantee that there will never be a value for this. Interesting. So if you check the IntelliSense, there's nothing. Obviously, after the if, well, we're outside the if, so we have no idea what happened. We have no idea whether or not we ended up on line 21 or on line 23. We know for sure we didn't end up on line 25 because that can't happen. So now we have again name, surname, kind, and age. This is called a flow type system, and it's, in my personal opinion, perhaps the single most powerful feature of the TypeScript type system that sets it apart already from most modern programming languages, which is quite impressive. Okay, now we're going to take a look at some even more exotic and advanced functionality that we have in TypeScript type system. We're not going to use anything special with respect to what we've seen already, by the way. So suppose that we want to model a state, and in our state, in the state of our application, then, well, we are loading something, an entity. Let's say that indeed we have a customer, and the customer has an ID, and that's a number, has a name, and that's a string, has a surname, and that's a string. That's quite simple. And we're loading a customer. Now, you might be tempted to state that we have a customer, and that's a customer. Now, TypeScript also allows us to define something to either be a customer or undefined, and there is a handy shortcut for this. It means that we might either have or not have a customer, and then we could have loaded, which is a boolean. Okay. Let me tell you why this is very wrong. Well, this state can be invalid in many ways. For example, we could have invalid1. Let's tell TypeScript that this is a state, so it helps us a little bit. So let's say that it's loaded. Yes, yeah, it's been loaded. And the customer is undefined. Ooh, that's an issue. We could have the opposite. We could have that loaded is false, and the customer is not undefined. And now I put an ID, and that's one, a name, and that's John, and a surname, and that's Doe. Okay, now, and that's something that we really want to avoid, because if you just look at this very simple state, now it's kind of, you can still kind of guess that customer and loaded will be correlated, but also not really, because loaded might also refer to something completely different. So let's do this properly. Let's say that the customer is something a bit more complex. It is a value of type customer when the status, I tend to use kind for everything, but you could also use status, when the kind is loaded. Or it can be unloaded. Then we remove the loaded boolean. Now inside the customer field, the customer attribute of the state, I have all the information relevant for the customer. So now, if I want to create my initial state of the application, and the IntelliSense is helping me, and now what I can do is I can put unloaded, or I can put something else. I can put a kind, and look, the kind is supposed to be loaded, and then we have a value, and the value is going to be let's say ID1, name is John, and surname is Doe. Okay, now suppose we have a function, I'm just gonna call it f because it doesn't really matter what function it is. A function that takes us into a state and wants to do something with it. So in the state we have customer, and oh look, we can't really say anything because it might be unloaded. And so now we're forcing anyone who's using the code to check properly, because, well, they must check. If they just get a state without any extra information, then they can't possibly know what the customer is, and we check if the customer is not unloaded. Oh, by the way, that's exclamation mark equal, but I have a pretty font that turns it into the mathematical symbol, so don't get alarmed. And then here, if the customer is not unloaded, then they have a value and a kind, which is absolutely awesome, because it means that whoever comes after you is not going to be able to make particularly tragic mistakes because you're helping them understand what your code is supposed to do. But let's say that between loaded and unloaded, there's, you could guess, loading. And when we're loading, well, we have a customer ID. So now I'm going to use multiple lines for this, and we could have a kind loading home, or sorry, no, that's disgusting. Customer ID, and that's again a number. And now, when I create a state, well, I could say it's loading. And look, the value is not a customer anymore. The value now is supposed to be, so we don't even have a value attribute, we only have a customer ID, and let's say that's 1. Now I'm kind of stating that a customer can be any of these 3 things. Can be loading, can be the customer, can be unloaded. And again, if you see what happens when defining a function that takes as input a state, and so this function doesn't know anything whatsoever about what S is. If I check S and there's a customer, and again, if I invoke the IntelliSense here, it tells me absolutely nothing. So I should check, okay, is it unloaded? And if it's unloaded, well, now I have the customer, and what do I have? Well, I have the kind, because I don't necessarily have a value or a customer ID. Why? Because I first have to check whether or not the kind is loaded. So let's take a look. If they're loading, then s.customer.customer ID, but I don't have a value. But in the opposite case, you might hear my children in the background. Hope it doesn't bother you that much. s.kind.value now has ID, name, and surname, which is what we were expecting. And in the final else, in the final conditional, then that's interesting. Oh, sorry. We should add we could add another check whether or not the customer is loaded. And well, here obviously we're stating the obvious, because if the customer is not loading at this point, they must be loaded. And now we have the ID, name, and surname. And again, so here we have a state, and the state has a customer, but the customer has type, again, never, because it's not possible to define, it's not possible to come on line 28. So s.customer has the type that contains no values. We can call it never, but we could also call it empty, which would be perfectly reasonable. We might also want to change this type definition. I'm going to remove this. We might change it so that it expresses the fact that we go from loading of a customer ID to loaded. So there's a sort of sequence, and well, the sequence of this, we could express it by nesting. So let's say that here we have the kind is could be loading or loaded. Then we also always have a customer ID that we're loading, and then, even though this is quite verbose, so I'm not really advocating doing this, I'm just showing the technique a little bit for the sake of it. And then we could state that the loaded value, let's call it the loaded value, is the customer and they're loaded, or we're still loading. Could even remove this kind if we wanted to. Okay, so now if we want to say that a customer is loading, then I have to specify the customer ID and the loaded value. Let's say that they're loading, for example, or alternative, that the kind is loaded and the value is then our customer. And well, in this case, it really makes sense to expect the name, the surname, and especially the ID to be in line with the customer ID. Now again, I'm not stating that this is strictly better, but it's a possibility that the type system offers us to enforce sequence. Because now this is kind of enforcing us first to provide this information, so we really have to provide this information. This information doesn't really disappear because that's the customer we wanted to load, and this is, well, whatever came as a result of the loading process, whether we're still going through it or we have loaded a customer and that's what came down. But it's sort of an audit trail, and you could keep nesting here. You could keep nesting here stuff if there's extra steps. So for example, if you don't have to submit something, you could have the submission, and you could say that the submission is submitting or submitted, and inside submitted you could actually have a kind submitted and whatever, you know, the data that we submitted, and let's say this is just a number, so otherwise it gets a bit silly. And now I'm saying that the lifetime of a customer, well, they're either unloaded or, well, first we have to load them, and after they're loaded, then, well, we have the customer, and then at that point we have a submission, and first we are submitted, and finally we go into submitting and we have the data, but we also have this nice trail. So let's, oh, did I forget a curly bracket somewhere? Probably or probably not. The loaded value should be, yes, actually looks in order. Well, let's find out what's broken. That's the big challenge of live coding is that stuff is going to break, even though so look, that's broken to me. Declaration or statement expected. Huh? Oh, I forgot curly bracket. Okay, so now let's take a look. So the customer, first thing we have to check is whether or not they're unloaded. We could even use the flow in a different way, that I simply return, and from this moment on, we know that if we end up here, this is the same as an else basically, because if the customer were unloaded, then we would have returned. Now we have a customer ID, so that's part of our trail. We have the loaded value, and let's check if the loaded value is loading, we can return. And now we have the customer ID and the loaded value, but the loaded value has a value. Now we check the submission, and if the submission is submitting, again we return. And finally, what do we have here? At the end we have the customer ID, again our trail, the loaded value, and the value, which is the customer. But we also have the submission, and in the submission we have the data. And well, that forces us to have the trail. But you could also imagine that this thing can have sort of forks. You could have customer, or I don't know, employee, or employee, which I don't have here, or product. And well, in this case you've kind of introduced a fork that's allowing you to define the structure of the sequence of state evolutions in a very, very precise way. This is incredibly powerful because now I'm really telling a story in my type about how this type is expected to be used. You can almost feel a user story here that says that a customer loads from a customer ID that must be selected from whatever, maybe a drop down or something else, and then the customer loads, and finally the customer, the loaded customer results in a submission of some data which is a number. This is very powerful. This is very expressive. Let's now conclude our survey of types in TypeScript by touching upon advanced types. Now, advanced types are something that's very abstract, and as such, it's very difficult to give examples that are immediately intuitive, so you'll have to forgive this. Just be aware that this exists, and we use it in some advanced libraries, but that's, yeah, all I can tell you. Let's begin by introducing key of. Suppose I want to define a function, let's call it the setter, and it's a generic function. And as a generic function, it takes as input some generic parameters. And let's say that I want to be able to set the field of a given type. So let's say we have a type T, and I want to change one of its fields. So I can say that the setter is generic in the type T and type F, but F is not just allowed to be any type whatsoever, but F must be a key of T. Now I get, well, the value which is type T, the key which is type K, and what do we return? Well, we still return a T. And oh, sorry, the key, and that's the field. Yeah, no, let's call it field. Key field attribute. That's all the same. Now we have the value, and we could simply return. No, well, we could define. We could return the value, but where the field has a new value. Now for the moment I'll simply state that the value is value of field, so this is simply, well, this is not really changing anything, but let's obviously also get a new value for the field. So the new field value, and what's the type of new field value? Now it's going to be T of F. So this checks inside the T what is the type associated with field F. And now, instead of value of field, I can put a new field value, and notice that the compiler is not really complaining. Suppose now that I have an interface person, or type, these two definitions are roughly the same. Actually, I'm going to use this one. I like it more. It has some advantages. And it has three things. Quite easy. And also I have, let's also define another type, address. And the address has a city, has a postcode, and has a number. Nothing very exciting, also I'm not really doing my best to think of intelligent types. Now I could call my setter function, const, well, okay. Person1 is a setter over person, and now, well, let's say that I try to put name. Now look, it wants a person, so let's print the person. Say that the surname is John. The name is John. The surname is Doe, and the age is 27. Okay. Now what's the next parameter? The next parameter is field, and the field can only be name. Look, it's actually auto-completing it for me. And what's the next value? Now the new field value, it must be compatible with whatever type name had inside person. So let's say that this becomes Jane. Let's actually print p1, or let's see if I can get the debugger running. Start debugging. And well, here we are, I guess. Step over the, okay, MP1 now is, oh look, age 27, name is now Jane, and surname is now Doe. That's exactly as we expected. That's good. That's actually very nice. So now we have a setter, and let's say that we put surname here. Oh, we get a compiler error because, well, this was supposed to be surname, and now Smith. And again, we have the same as we had before. So now we're changing the surname field of person. Suppose that we put something else. Suppose we put city in here. Now it's going to give us an error because it says that city doesn't satisfy the constraint name, surname, or age, because those are the only keys available in person. And indeed, no, we can't see them here. We can put age, and then the error is, it moves here because then these types are compatible with each other. But then this bit of code doesn't make any sense. And if I put the age, now it complains. Why? Because Smith is a string, but the age is connected to a number. So I could put 26 here and we'll be happy, but not a string. TypeScript is smart enough to allow us to remove that declaration. So in this case, just by looking at the first parameter, it's able to guess that the only things available are age, name, and surname. I could put name here, and now it's going to give us the error exactly where the error is supposed to happen. So that's very nice. We can also play around with the structure of something like the setter by, for example, first taking as input the t, and then taking as input the field, or the other way around. We can. There's a lot of things that can be done with a structure like this. My personal preference is to well, separate, for example, this way. To separate the definition this way. Then first the setter gets all the context, which is the value and the field, and then it gets the new field value. There's also something to say for splitting it even more aggressively. So first we get the context. So we might want to put the type annotation on this, but this we really want the compiler to guess, because otherwise it's very repetitive, because f and field are always going to be the same. Or we could let these two merge, and then what we can state is, for example, p1, and this allows us to put a minimum number of annotations. So we could say that there's a person here. I'm going to do something ugly. I'm going to put a null exclamation mark, which is very evil, and you should never do it, but I'm too lazy to want to type a person at this point. And now it knows that the only things allowed are name, surname, and age because of this annotation, and because I've told it person, we're not relying on the type inference of TypeScript to guess from whatever object we put here what type it's supposed to have. But indeed, now we can say that we want to change the age, and here we're supposed to put in a new field value of number. And look, if I turn the age into name, now it says the new field value is a string. And again for the surname, and let's put Smith here, and it's happy. Okay, so that's very nice. Another very simple experiment we can run is that if I put in an address, again I'm too lazy to put in here a proper address, and we get a compiler error here because it says no, because the surname is not assignable to number, city, or postcode, which are the only attributes valid for the address. And again, if I invoke the IntelliSense, then city, and let's say that the city becomes Rotterdam, so the thing is happy now. If we were to put in the number here, then I obviously get a compiler error because Rotterdam is a string, and this is incompatible with the number. Now, let's move into a realm which is perhaps even more abstract. So let's say that we have a series of ageable things. So we have a person, they have an age. We have wine, which has a kind, white or red, and also an age in years. And we have aged cheese, I guess. Okay. Now let's say we have a house. Houses also have an age, and that's kind of relevant. And I'm just putting the age here. Obviously, they should have something else. Now let's say that I put the ageables, and I say that the ageables are person. Just type person. So I'm building a registry of all the things that can age, all the things that have an age in the application I'm building. Okay, now I want to define a function that increments the age by 1 of an ageable. So let's make a first attempt. Increment age. So increment age. What are we supposed to get as input in order to be able to increment the age? Now, something with an age, but I really want to increment age to only work on our ageables. So let's say that the entity that we get for the ageable must be one of the keys of ageables. Now, increment age is going to take as input, well, a value v, and this value v will have type ageables of ageable, and it will also return an instance of the same thing. Let me be lazy for a moment. Let me return null exclamation mark. Now, what is this saying? This is saying that increment age, we specify which ageable we want to actually age further, and then it takes as input from the ageables. It picks whichever of these it was and returns a new instance of it. So let's say that x comes from increment age, and all we can put here is only person, wine, or house. And here, oh look, now it knows that it's supposed to be a person. So, well, again, let's give it exclamation mark, and it also knows that x is a person. It could also be a wine, and now the input is supposed to be a wine, and what we get out of it again is a wine, so x is a wine. So by just changing a string like this, we can define which ageable we're going to run. But we could also make this more complicated. We could define a function that takes as input just the ageable, and let's also say that we pass it as a string or not, it doesn't really matter that much. And this function can now call increment age on whatever it wants, without ever knowing which ageable we're really talking about, because, well, when we call it here, we're completely dependent on the type ageable that was given to f. Now, the code for increment age is actually not that exciting, as a matter of fact. Well, let's make an attempt. I'm not going to fight it that much. When doing things that are at this advanced level of type safety, it might sometimes be that for the signatures and the code can't match each other. It shouldn't be the case now, but let's try. So let's say that we take v, and then we put the age, and v, and age is going to be v of age plus 1. That is truly, oops, v of age plus 1. Now, here we can actually see how smart the compiler is, because, well, it knows that v is an ageable, and it knows that ageables of ageable, the only thing it has is an age, because, well, that's the only thing they have in common. We could actually even just write v.age as a matter of fact. And so here I rebuild v, I copy v over, but in the age I put v.age plus 1. And thanks to this technique, you can get incredibly far by combining keys and lookups. And notice that the ageables type has no function whatsoever. It's never really going to be declared. It's never going to be instantiated ever, and it's never actually going to find its way to JavaScript files. The only thing it does is it contains a registry of the things that are allowed as the first parameter, as the generic parameter, to increment age. TypeScript really is quite an amazing language, if I have to be honest.